So we've already covered the different types of amino acids. We've covered the way we classify them into polar and charged and unpolar. We've also covered how they bond. We've covered what the peptide bond is. So now we're going to talk about what peptides are. And that's a very simple definition. A peptide is basically a polymer of amino acids, right? So it's a very generic term. Proteins are one kind of peptide, the kind that you might be most familiar with. So the recurring motif, which just means a common theme or a common structural component of a peptide, is the peptide bond, right? So the peptide bond is like this. This is some amino acid. It ends in a carboxylic carbon, and then it goes off like this, and then you have the next, and then you have the amino group of the next amino acid. So this is what we know as a peptide linkage, right? This is what we know as a peptide linkage, and as you can see, it can be reversed by hydrolysis, because this is clearly an amide and it is formed by the elimination of a water molecule. So this is the recurrent motif. Now when we talk about peptides here, this is an illustrated version with the things in different colors. How would I name a peptide like this? How would I go about naming this peptide? First, let's check what it is. So we can see that it is, we've got the amino group, the carbon, a hydrogen, carboxyl carbon, amino group, carbon, hydrogen, carboxylic carbon, which is here part of an acid. And on this we have a side chain, which is just hydrogen itself. So this is clearly glycine. And over here we have a side chain, which is the methyl group. So it is clearly alanine. I hope you remember these names from the previous section. Glycine especially you're supposed to remember because it is the only achiral one. If you remember, if you look over here, then you can see that this carbon, the carbon of alanine, is clearly chiral because 4 different substituents, but the glycine has 2 hydrogens and is therefore the only achiral amino acid. So when we talk about this, when we want to know how to name this, it's very long-winded to use the entire IUPAC name. So what we tend to do is we use the 3-letter codes that I told you about last time, and we call this GlyAla. So this is known as GlyAla. Okay, and there's a friend of mine who actually refers to these as nicknames of amino acids because they're quick, and this is how you will most commonly see something written. Also, you can often see the first letters of the amino acids will be capitalized in some conventions. They'll be left lowercase in some conventions. But this is how we generally talk about a peptide. So you might be given a problem that says that this peptide, and then just rattle off 5 nicknames is something, and then you're asked to solve some question to do with that. This is how we nomenclate the peptide. Also, you should notice that this is not commutative. I cannot just reverse this around. Okay, GlyAla is not the same as AlaGly. AlaGly would be an N-terminal alanine and a C-terminal glycine. This is an N-terminal glycine and a C-terminal alanine. What does that mean? That means that if I look at this glycine, the nitrogen can be attacked by the carboxyl group of another amino acid. So here you can polymerize through the nitrogen. And if I look at the ALA, right, then for the ALA we can see that over here this COOH is still here, and this can react and form an amide with another amino acid's amino end. So this is the N-terminal and this is the C-terminal, right? So when you have GlyAla, that's N-terminal glycine, C-terminal alanine, and then the opposite is vice versa. So don't get confused. The two of them are entirely different things. The two of them are not interchangeable in any circumstance. Right. So the next thing that we need to understand is that this peptide linkage is not a simple single bond, right? So this is something you may have studied when you were studying about amides in general. When we look at the structure of an amide, there's going to be a resonance of sorts, right? If this is the structure of the amide in the common form that we see, then you can also have this sort of shift in electrons, and what you will get is a structure that looks like something like this. You get a structure looking like this, right? And this can be denoted as a coordinate bond if you want to be precise. It is in fact a coordinate bond. So what's happened is we've been able to switch this into this, and because it's resonance, it's going to exist in a superposition of these two states. So what kind of superposition of these two states will this be? Well, we know that these carbon double bond O structures are very stable. They generally are, they're generally favorable with a lower potential energy. So this contributes 60%, and this structure contributes 40%, which is why we have said over here that this has a 40% pi character. Okay, it has a 40% pi character, and that means something. That means that there's not going to be any rotation allowed around this bond. So maybe I should so I've boxed that bond in purple here. Unlike any of the other bonds that are part of this long chain, this bond has no free rotation around it owing to its 40% pi character. Okay, remember that if you've got, say, if each of my hands is an atom and you have this sort of bond between them, then there's no problem because they can rotate like this freely around the bond. But at the same time, if there are two bonds like this, okay, let's assume that one edge, the upper edge and the lower edge are two different bonds, then when I start to rotate like this, one of the bonds will come off when you're attached by two different bonds. So whenever there's any double bond character, it's not possible to have free rotation. That's very important. It's one of the most important things that you learn when it comes to peptides, when it comes to polymers, that this bond does not have free rotation due to this resonant characteristic. Okay, next we come to the protection of these groups, right? So what do I mean by protection? I mean, say we've isolated some fragment of protein, okay? We've isolated a fragment of protein, and now we don't want it to be, we want to mark what was at the C terminal and what was at the N terminal. That is, we want to mark the terminal residues. So this could have gone on for any length. You could have 5, 6 amino acids in the middle, but there will always be an N terminal which has 2 hydrogens and a C terminal which has 2 oxygens on the opposite ends of the peptide chain. So for instance, if I take this glyala over here and I want to make it so that this N terminal will not react with anything further but will remain as the N terminal, it will remain a terminal amino acid and will not take part in any further polymerization with other amino acids, with other peptides which are floating in my mixture, I will apply a protective reaction, just like we have done protective reactions in in aniline and all the other compounds we've dealt with so far. So as you know, with aniline, which is also an amine, as we're aware, what do? We add acetic anhydride, right? So let's see what happens over here. When I have acetic anhydride, plus so we have acetic anhydride plus an amine group, then we know that what's going to happen is that you will have this. We get this sort of structure. We get this acetic we get an acetylated amine. So when we get this acetylated amine forming over here, and one of the hydrogens will go, other hydrogen will remain. Okay, then you can clearly see that this is not going to be capable of amide formation no matter where your other amino acid comes from. So say you've got a mixture of proteins and you've broken it down using some enzyme to this particular dipeptide, and now you want to study this dipeptide. So then what you're going to do is, or say you've got multiple different dipeptides you've broken it into, because you have some enzymes that will break off a long protein by chopping it every 2 adjacent amino acids. Now you want to study all these chopped off pieces one by one, and then you're going to try and figure out what the sequence of them is. You don't want them going and binding to each other and messing up their sequence. You're not going to be able to study the protein that way. So this is one very good way. As soon as you've chopped it up, you apply AC2O and the N terminal gets blocked like this. There's another thing that we do. That other thing has to do with PHOH at the C terminal. So that's not hard to understand. You can see that if you have phenol, that's an alcohol, as you know, and we have any kind of carboxylic acid, then we know that the reaction which is going to take place is esterification, right? So we're going to have this esterification reaction, and we're going to be left with PHO C double bond O, or carboxylic ester. So what ends up happening is we get an acetylated or an amide of some sort at the N terminus, and we get a ester at the C terminus. And because of this, if these are connected, so if this is connected at the C terminus and the other one is at the N terminus, then your entire peptide, whether it be a dipeptide or a tripeptide or whatever length, is going to be protected at either end and cannot undergo further polymerization. Okay, so now the last thing we need to talk about here is the different lengths and how we classify them, because we do classify these peptide units on a length basis. So if you've got something like this, where you've got just two different like gliala, two different peptide units, two different amino acids, it's known as a dipeptide. Which is a term that you've seen before, so I hope there's no surprises here. Similarly, when we have 3 to 10, it's an oligopeptide. Oligos mean Greek for few. So oligos, few peptides, few amino acids long, oligopeptide, 3 to 10. A typical protein is a high polypeptide. That by high I mean that it has a high number of monomers. I don't mean anything else. So 100 to 1000 is a typical range of amino acids in a protein, which, as we'll study, is a complex biomolecule with a lot of structural attributes that only arise when you have many amino acids linked together. There are some exceptions which are on the low end, and one of them is insulin. So insulin is an important protein. We will come back to it again later on. We've already mentioned earlier when we were studying polysaccharides that insulin has an important role to play in that it directs the body as a hormone to say, okay, we have enough glucose in the bloodstream, start storing it. And we already covered how it doesn't tell the individual tissue whether to store it as glycogen or whether to store it as fat. And that's a tissue by tissue response. So insulin is actually amongst the hormones. It's one of what they're called the peptide hormones. It's a peptide hormone, which means it's a hormone. It performs regulatory action, but it's actually structurally a protein, because we have hormones that are lipid hormones and we have hormones that are peptide hormones. So this is a peptide hormone, and it is one of the smallest proteins there are. It has only 51 amino acids, whereas the most of them, as we say, have hundreds upon hundreds of amino acids. So in the question that you were asked to solve, you were given that there was a 7 amino acid peptide chain, so it's a 7AA peptide, and you were asked how many water molecules are required in the hydrolysis of this peptide, of this oligopeptide. And your options were A7, B6, C8, and D, none of the above. So you can work this out in a very simple way. What does that mean? What it means is, if each of these are a peptide unit, so this is written amino acid again and again and again. Ultimately, one amino acid over here will have an N terminal, right? This is an N terminal. Which is basically NH2. This amino acid over here will have a C terminal, which is what? C terminal is just the presence of a COH. The C terminal is just the presence of a COH. The N terminal is just the presence of NH2. What about all these in the middle? All of these have amide linkages. C double bond O N, that type of linkage, right? If I want to keep the color choice consistent, maybe I should C double bond O N. So this amide linkage is present in between each of the amino acids. Only at the very endings do you have these missing. Each amide linkage forms from what? It forms as a linkage between two amino acids. So if I have 4 amino acids in this illustration I've made, then between the first and second and third and fourth, I will have these peptide bonds. The end chains would have they would have one more bond if it was a cyclic peptide. If this was a cyclic peptide, then there would be a final bond over there. So if they would, then in that case, just like any cycle, like a polygon for instance, n vertices, n sides. Since it's not cyclic, that means one side is missing. So that if you had geometrically, if you had like a pentagon and you remove one side, this is exactly what we're doing here. It's an n amino acid long chain, but the last and the first are not connected to each other. So it's like a polygon with one side missing, right? So then you would have n vertices, but n minus one side. Similarly, you have n amino acids, in this case 7 amino acids, but you will have 7 minus 1, 6 peptide linkages. To break each peptide linkage, you will need one. To break each peptide linkage, you will need one water molecule, and therefore to break 6 peptide linkages, you will need 6 water molecules. The answer is B. Alright, so this question is actually one that is based on the previous question, and it's important. This was a question in JE 2011. So the question goes, a decapeptide comprising alanine, glycine, and phenylalanine with the total weight or total atomic mass of 796 U, unified mass units, is hydrolyzed. Now the glycine in this, the glycine residues make up 47% of the hydrolyzed product weight by weight. Okay, what is the number of glycine amino acids? So this is very simple actually. The only trick over here is to realize that when you're hydrolyzing, you must be adding 9 different molecules of water, or you won't be able to get decapeptide hydrolyzed. So total weight of the hydrolyzed product I'm just using HYDR as an abbreviation for hydrolyzed product. Total weight of the hydrolyzed product is equal to 796 plus 9 into 18. 796 plus 9 into 18. Okay, now we know that glycine is 47% of this. So the weight of glycine the net weight of glycine, the total weight of glycine is going to be 47 by 100 into 796 plus 9 into 18. This is the net weight of all the glycine amino acids combined. Okay, but we also know what the weight of just one glycine is, right? So if we want to get the number of glycines, we're going to take this. Let me just denote this by the symbol W, because it's taking up too much otherwise. So if you want to know the number of glycine amino acids, we're going to have to take this total weight and divide by the weight of one glycine, right? How much is the weight of one glycine? The weight of one glycine is going to be 75, which you can calculate by adding up the weight of all the amino acids. As it is, the structure of glycine is something that you should be familiar with. So we're going to get number of glycines is equal to this quantity W, which we have defined here, divided by 75. This will approximately come out to be 6, which is the answer to this integer type question. Okay, so now we're going to be talking about Phi, Psi, and Omega angles. Okay, so basically we're going to be talking about something that doesn't strictly fall within the syllabus. Okay, it's a conceptual framework that's going to be very useful for explaining secondary structures which do fall within the syllabus. You're expected to understand this but not remember it, just like you weren't expected to remember all 20 amino acids. Okay, so what are these angles? These are basically just dihedral angles. So you're familiar with the concept of a dihedral angle, obviously. A dihedral angle is what? When you've got two carbons like this which are connected along a bond. You have a carbon here and a carbon here. What is this angle around this bond? It is some angle theta. Okay, then that's your DHA, it's your dihedral angle. What is the angle between this substituent and this substituent? How much I need to rotate from the angle at which this substituent is found to get to the angle at which the substituent is found on the opposite carbon along this bond, right? So when we look at a peptide chain, right, we have three kinds of bonds that form along the backbone. You have the nitrogen to carbon bond of one amino acid, of a particular amino acid. You have the carbon to carboxyl carbon bond of the same amino acid. And then you have the peptide bond between adjacent amino acids. Okay, then again nitrogen to carbon bond, carbon to carboxyl carbon bond, peptide bond, it just repeats. So there are basically these three different kinds of angles. So instead of using a term like theta, we use three different variables: phi, psi, and omega. So we'll talk about what values these angles assume and how that helps us understand the kind of conformation in which the whole peptide chain will tend to exist. Right. So each of these dihedral angles, phi, psi, and omega, we can see by use of one of these projections, these Neumann type projections. So let's see what this tells us. Okay, so for the phi angle, if we look along the peptide bond, we have to look, not the peptide bond, sorry, along the peptide backbone. If we look along the backbone from the N terminal towards the C terminal, then you will have the nitrogen in front of you and the C alpha right behind it, right? You're going to have a nitrogen in front of you like this, and the C alpha will be right behind it. So that's exactly what we see over here. The one written above is the one written above inside the circle is the one that's facing you, and the one written below it, C alpha, is the one behind that particular atom. So you have 2N is the second amino acid nitrogen facing you, and right behind that you have 2C alpha. Now 2N has a particular substituent, right? What is the substituent? It's the substituent along the backbone. We never take this H or this R or this oxygen or any of these others to be the substituents that we're interested in. The DHA is always between the different substituents that comprise the backbone. So what is nitrogen bonded to? That is part of the backbone. Nitrogen over here is bonded to 1C, right? Because the carboxyl carbon is C, whereas the other carbon is C alpha. So 2N is bonded to 1C, and 2C alpha is bonded to 2C. 1C and 2C. So we can see that the two of those will have an angle between them, and that angle, which when we view along the bond, is called the Phi angle. Okay, so let's see if we can see this in terms of a model. If we look at a model like this is the bond we're interested in, right? This is the nitrogen over here, and then the C alpha carbon over here. So if we look at this bond, then we can see that this guy, let me show it accordingly. So this will be the bond to 1C, which is shown up here. If I make it on the same side as the diagram, you'll be able to see it clearly. So this is 2N, this is 2C alpha, this is the bond to 1C, right? This is the bond to 2C alpha, and to 2C, and you can see that there's going to be an angle between them, right? And this angle between this bond and this bond, this angle that you see over here in this plane, that is the Phi angle. Okay, the same thing is applicable. The same is applicable to the Psi angle. What happens in the Psi angle? In the Psi angle, we view along this. So the 2C alpha is the carbon that's facing us, and 2C is behind it. 2C alpha is bonded to 2N, whereas 2C is bonded to 3N. This you can pause the video for yourself and verify that I have drawn this correctly, right? So 2C is bonded to 3N, and 2C alpha is bonded to 2N, and there's going to be an angle between them as well. And this angle is the Phi angle. Okay. Now you must understand that these angles have a maximum magnitudinal limit of 180 degrees. So if instead of being here, if the 3N was somewhere here, then if I went in this sense, right, what sense is this? This is the clockwise sense. If I go in the clockwise sense, then I will get an angle that is more than 180 degrees, is it? Okay, here it's still less because I've drawn this to be on this side. So if I come till here, I get an angle that's more than 180 degrees, right? So instead, we'll use a negative angle. So if this is 190 degrees, we will write it as minus 170 degrees. So we always use the flip side. We always take the shorter distance. shorter angular distance. So if it's not coming out to be clockwise and positive, we'll use the anti-clockwise and therefore the negative sense to measure it. Okay, so that's the phi angle, that's the psi angle. Now let's come to the third of the three angles, the omega angle. Something might already have come into your mind with regards to the omega angle, in that it's not like the other DHs. In what context do we normally study a dihedral angle? In the context of conformational isomerism, where you have freely rotating structure. So if these three chalks represent something like this, I don't know, I hope you can see it. These three chalks represent a structure like this, then when this chalk and this chalk have an angle, the pink chalk and the yellow chalk, and then I can rotate the yellow chalk like this, and I can change what the angle between the yellow and the pink chalks are. But that is not going to be possible. That's not going to be possible when it's the omega angle, because the omega angle is along this. It's along a partially pi character bond, right? We have this resonance over here. It's 40% pi character. It's got a 40% double bond character. So you can't rotate freely around it. Whatever value it has, it has. So when we come to the omega angle, we see that there's a particular structure like this, right? So omega is which angle? It's between C and N. So between C of some peptide. So this is 2C and 3N, right? Which was the bond over here. You can see 2C and 3N over here is behind when I view along this axis. Now what I'm doing is I'm viewing along this axis. So when I'm viewing between 2C and 3N, they're going to have this partially double bond like character. So I can classify them as cis or trans, right? So typically to avoid repulsion, they're trans. Let's see how that works. This carbon is linked to the C alpha, which is in turn is linked to an N, and over here it has an R on it. This nitrogen is linked to the next C alpha. So this is 2C alpha, then this will be 3C alpha, right? So these are the two different carbons like this. Now, what you should remember over here is that this C alpha also has an R on top of it. This is another R. And if I look at it like this, these R's will be going into the plane, and so they're likely to bump into each other if they're on the same side. But probably I made a mistake over here. Because the C alphas are on opposite sides, the R groups attached to them also go off in opposite directions, and they don't tend to bump into each other. That is why this is much more stable than the other one, and therefore the majority product when you join two amino acids into a dipeptide is always trans. That is, omega is equal to 180 degrees. But you can have like 10% of residues which have proline are actually cis. I'd encourage you to pause a moment, go back to the structure of proline, and think and see if you can figure out why this should be the case. 10% of cis is present in the case of proline, as I just said, and you were asked to find out why based on the structure. Now, what you'll see is that if I have a proline residue, then ultimately this R group is going to contain a bond back to this nitrogen, right? So it's even when it goes out into some plane, like say in the case of proline, what is the structure of proline? I hope you remember. It's like this. So this is the carbon that comes out. It'll go tuck, and then it'll bond back to the nitrogen. So if this is the nitrogen over here, then it forms one vertex of a pentagon, right? If this nitrogen weren't there, then this could go out and flail about like this, and then when I'll have the R group of the previous guy, which will be coming from somewhere here, then they could collide. They could get entangled. But when I have this nitrogen, it provides this stabilizing thing. It holds the proline back, and that makes it a very good anchor. It makes it very stable, and therefore it is an ideal, how should I put this? It's one of the ideal things when you want to have cis dipeptides, and 10% of polypeptides or dipeptides that include a proline at a given place will have an omega equal to 0 or an omega approaching 0 value because it is cis, right? So this is something that happens because of the presence of proline. It's very important. It's very often used, like there is a secondary structure, a particular kind of polyproline helix. It's a particular structure of proteins that relies on having many prolines which are constantly in the cis isomer. It gives a certain flexibility to the ring. But typically, proline has its own constraints, which we'll study about going forward. So what I need to know is that you know the phi angle, is the first angle, then the psi, then the omega. If you just remember this order, and you remember what the three things are: nitrogen, C alpha, C, nitrogen, C alpha, C, you'll immediately remember what these guys are between. And you just need to know the partial pi bond character to derive the fact that omega will typically be in the 180-degree state. This is something that you remember, that proline can adopt a cis conformation. So just to give you an idea, if this is my entire structure, then this is going to be my N-terminal, C alpha, then this is going to be my peptide bond, right, over here. So let's see what happens with this peptide bond. Obviously, this is not, as I said before when we were doing sugars, these ball and stick models don't cover sp2 hybridized carbons, only cover sp3 hybridized carbons, but we'll work with that as a limitation. So what does this thing tell us? If the peptide bond is truly has this sp2 hybridized carbon here, then all of this peptide bond, this entire thing should be planar. It should be planar. So whatever the nitrogen is bonded to, whatever the carbon is bonded to, it should be in the same plane and it should be trans, right? So this C is bonded to this C alpha. We can see that over here. This N is bonded to this CR. So just like this is an omega, this will also be an omega, right? Just like this is an omega, this will also be an omega angle, right? So when we're looking at this omega angle right now. So to bring it back to where we were, this is my C, this is my C alpha, good, C and right, so C and C alpha, and then here I have my nitrogen, and then the next thing I'm going to have is I'm going to have the nitrogen bond to the next C alpha. So these have to exist in this trans conformation like this, and this is going to keep repeating in all of them, in every next amino acid. So I hope you can see that this ladder-like formation is slowly starting to approach, and if you put the N-terminal at the bottom as is traditional, you can see the kind of shape it's going to assume, and that's going to be very important for us because you can see that this is slowly going to twist back on itself, this structure. Okay, so now we're going to be talking about something known as secondary structure. Okay, so if you're moving on to secondary structure, you might be tempted to ask, what did I mean by primary structure, and why haven't we covered that? Well, actually we have. Primary structure is just the sequence. Primary structure is also known as the sequence of your amino acids. So Gla, Yala, Fe, etc., etc. So when you have that sequence, the structural formula that you guys draw, that you have been drawing throughout organic chemistry, complete with the specifications of your how should I put this? Complete with specifications of stereochemistry, absolute stereochemistry, that entire formula is known as your primary structure. So this is the sequence and connectivity, how each of these atoms are connected to each other and with what configuration, R or S, D or L, are they all connected to each other in a primary structure or in a sequence. Some people say primary sequence. That's wrong. They're mixing up two terms. It's either called the sequence of the protein or the primary structure of the protein. But now we're moving to what is called the secondary structure. Okay. Now the secondary structure is not something entirely new. It's just that it's not worth defining for the molecules, the tiny molecules that we've dealt with so far. In the tiny molecules we've dealt with so far, we've come across conformational isomerism. In some cases, we've seen that one particular conformational isomer is heavily favored over another. For example, in the case of 8-annuline, we know it will never take the planar configuration because that will make it anti-aromatic. And in fact, it will choose to decompose as soon as possible into some more stable compounds. So, but setting that aside, typically we haven't had to consider conformational isomerism in a big way. In a protein, however, you can have a long lasting chain. So remember what we did with the structure of cellulose. It was a sheet, right? We had this various sheet-like structures that were all, these sheets had hydrogen bonding amongst themselves. So we have, these are called pleated sheets. This is a pleated sheet structure. It's pleated just like, when you pleat something, because it has all these knots entwined in it, and it has a slight right-handed twist that we can ignore for now. Basically flat sheet-like structures. That's assumed when you have one kind of conformation. If you remember what happened in cellulose, what happened is that every alternate ring was being flipped around, and that's what gave it this kind of conformation, right? But when we come to, if you remember, there was another structure that we had with cellulose, and that was a left-handed structure. A left-handed helical structure. This is not cellulose, this was amylose, if I remember correctly. That is also a possibility. So you have helical structures, you have flat sheet structures. We have all these different structures that arise based on how your conformations are, what the exact dihedral angle values are. That is known as your secondary structure. So the folding of this is known as protein folding in technical terms. So this folding based on the dihedral angles into a particular form is known as your secondary structure. Now, if we talk about, and these are stabilized mainly by hydrogen bonds. So a particular conformation, particular series of conformations will favor strong hydrogen bonds and it will be stabilized. If it doesn't, it won't. It's as simple as that. But how are we going to study these? Well, we know that you could have 3 degrees of freedom, your phi, psi, and omega. We also know that omega barely ever varies. It's either 180 or it's 0, right? And for the vast majority of them, it's 180. Only certain proline segments have a value of 0. So let's just, instead of having a 3-dimensional graph with full surfaces, we can look at a 2D graph where we are only varying phi along the x-axis and psi along the y-axis. And what we can do is we can check what kind of values, what kind of dihedral angle values are found in a particular conformation. So you can see that there are some clusters of values. There are some values here, some here, some here, some here, some here. So I can see 1, 2, 3, 4, 5, 6, 7, 8 different kinds of structures that we are considering here. Ultimately, only 3 will be really important for what we're talking about. But I'm just giving you an overview. So say you've got some long protein, and you can see that a particular section of that protein has all its dihedral angles in this area. So then you can say, okay, it's going to have a structure known as an alpha helix, which is a type of left-handed helix. Or we can say it has these types of structure, this particular set of values. And therefore, we'll say that it's what's known as a beta anti-parallel sheet. So we have all these different secondary structures which have to do with shapes like sheets and helices that these proteins will fit into based on their DHA values, their dihedral angle values. And there was this guy called Ramachandran. He worked at the Indian Institute of Science in Bangalore. And he and a team of his worked out what kind of values of dihedral angles different amino acids favor. So he tried to create a protein made entirely out of glycine, a protein made entirely out of proline, and so forth. And by doing that, he managed to get certain data. He managed to see what the exact preference of each amino acid is, and he constructed a plot like this for each amino acid. Here I have superimposed all those plots for you. This is the Ramachandran plot without qualification. So this is all the different regions where we've seen if you link up a bunch of amino acids, they may take dihedral angles. But then if you do it for just individual amino acids, you will see that each of them will only occupy a specific region of the plot. What is the advantage of this? By doing this, Ramachandran was able to identify which amino acids were comfortable in which regions of the plot, which amino acids had the least steric hindrance in which regions of the plot. And once he was able to identify that, you can, without looking at this plot for each and every individual protein you're making, you will know that, okay, these amino acids will tend to favor this particular structure because those amino acids tend to occur in this area. And then in any generic polypeptide made out of all kinds of amino acids, if the dihedral angle values are in this area, it's going to be helical. So then you can say, okay, these particular amino acids tend to occur in this region of the plot. That is, the dihedral angles roughly have these values. So say minus 55 degrees along psi and minus 60 degrees along phi. So minus 60, minus 55. That's the alpha helical region. It's one of the structures we're going to study. So you know that certain amino acids, say methionine, tend to have DHA values in this region. Then you know that this particular protein has a long chain of methionines at some place or an area where there's a lot of methionines. So then you don't need to again try and assess the DHAs of each and every one of those amino acids in that polypeptide because you know from the Ramachandran plot of the individual amino acid what it tends to favor, what kind of conformation it tends to favor. And just by seeing that, okay, these are the amino acids present, this must be the secondary structure, is a conclusion you can make. So let's take one of these various regions of the plot and analyze its behavior in detail. This is the right-handed helical region. Okay, the most common example is an alpha helix. We'll cover a few other examples as well. So what happens over here is that you have this right-handed helix. You can see it's right-handed, right? So if this is the N terminus, this is the C terminus. Remember, A protein is always depicted as going from the N terminus to the C terminus. So if this were a staircase and I were at the base of the staircase, then clearly it would be on my right. Now what happens here, say this is N and something else, then there's a carbon, double bond oxygen, and then there'll be another N, carbon, double bond oxygen, and so forth. In the middle of this is going to be a C alpha, the carbon that is alpha to the carboxyl carbon, or the carboxyl carbon here. What is the substituent on this carbon? It's an R group, right? Now, the nature of an R group is, over here, because this is left-handed chirality, L chirality, is that, and this is, by the way, okay, there's something important to clarify. There is a left-handedness of a helix, and there's the left-handedness of the individual molecule. The molecule has L chirality, it's a left-handed molecule. By that I mean the individual amino acid. Once it has polymerized, the left-handed chirality, the L nature of all the individual amino acids, gives rise to a right-handed helix. Okay, so when I'm referring to L chirality here, I'm referring to and only to the individual amino acid. Let's see what's happening. If I place myself here at the molecular level, just imagine that you could zoom down to that level and actually place yourself there. Then this N and this C double bond O, if I come from this angle, say, from a slanted angle if I look, then this N and the C double bond O are both approaching me, right? So it will be like this. We know what this is. This is just the Fisher projection. And we know that if we do a couple of switches for the L chirality, the R has to be over here, right? So let's see what that translates to. In this particular case, the N is going to be on my right. The C double bond O is going to be on my left. That's exactly the opposite of this diagram. When we make the switch, the R is going to be downwards. So the R is going to be pointing down and out of the helix. At every point, for every single amino acid along this right-handed helix, R goes down and out of the helix. When they're pointing outwards, since these can be long chain carbons, I've shown them with small green balls, but actually the R groups are long chain carbons. Okay, when they point outwards and downwards, it's much more stable for the helix than inwards and upwards. And the reason they point outward and downward is because of the L chirality, the left-handed chirality of the individual amino acid, which gives rise to a right-handed curve. Now the question is, how many amino acids do you have per turn, and why should it stay this way? Two questions, right? How many amino acids per turn, and why should it stay in this structure? So let's answer the second question first. Because the answer to the first question is variable. Okay, so as you remember from what you saw before, the double bond O's, they point slightly upwards. If I were to change color for them, right, they point slightly upwards. Now what's going to happen is we're going to have these amino groups, right? There's going to be an amino group over here above this, let's say here, and the hydrogen of the amino group is going to form a hydrogen bond with this O. There's going to be an amino group here too, hydrogen bonding. Amino group here too, hydrogen bonding. So we can see that there's going to be this kind of hydrogen bonding taking place, and these kinds of helical formations are favorable at this value of the dihedral angles, which you can check by making the model for yourself. This is just pure geometry, really. Okay, so what it says here is that if you come to around minus 60 degrees along the phi axis and minus 55 degrees along the psi axis, you get to this region, the alpha helical region. In an alpha helix, okay, in an alpha helix, you have 4 amino acids per turn. That's almost, quite a few. I think that's around 13 atoms per turn. Okay, and so if I ask you to characterize the hydrogen bonding of this helix, you will say that a hydrogen is going from the I plus 4, from the I plus 4 H NH2. These should all be NH, sorry, just single H, because these are all bonded. From the I plus 4H NH to the IH C double bond O. That's how it is. So for every one of these, we're getting a bond from the 4 amino acids above. The interesting story is that this wasn't the first model that scientists came up with. Scientists initially thought that this is only that it curves every 3 amino acids or so. There was even a paper published about it. One of the authors of this paper was a scientist named Bragg, and he's the son of the Bragg who worked on X-ray crystallography, which we will have studied in the solid state chapter in the beginning of 12th. So he and his friends published this model, but there was a lot of steric strain when there were just 3 of them per curve. A lot of the R groups, even though they're pointing outwards, they do tend to clash with the upper rung because it becomes too tight as a helix. And then Linus Pauling, with whom you should be familiar because he is the one who came up with the Pauling's electronegativity scale. Linus Pauling had a cold one day, and he was lying at home in bed, and he was trying to prepare a model of this using origami. So he tried to keep all the peptide bonds planar. He did everything the way we do, and he tried to create it such that the H bonds are forming these favorable rings. And he ended up creating, while lying sick in bed, this model, which is completely free of steric strain, and that got published, and that is the current accepted model. It's called the alpha helix, and the vast majority of helices actually end up taking this structure. So crazily enough, this was discovered, and this is a rebuttal to the original thing. But reflecting the good spirit of science, one of the authors on the original paper, who thought it was 3 amino acids per turn, he read Pauling's theoretical paper, and he came up with an experiment, and he went and confirmed it. So one of the authors of the original paper actually still managed to take credit for the 4 amino acid turn because he's the one who experimentally confirmed it. The reason I bring up this 3 amino acid turn, apart from the fact that it makes a good story, is that it wasn't quite ruled out. If you can see, there's a small region marked here as 3 sub 10. A 3 sub 10 amino acid helix has just 3 amino acids. That's roughly 10 atoms per turn. But because they're tighter, they're less stable, and they're often used where you want a really compact helix, or you want to make a very quick turn. So if your protein structure, look, I've drawn these to be really big, but I hope you understand that if I've got a protein, right, so if I've got some sort of protein over here, say it forms a sheet-like structure here. So it forms a sheet-like structure here, then it makes a turn, then it goes into an alpha helix like this, then it makes a turn. So this entire structure, and then it will come back in 3 dimensions. Maybe it will make another alpha helix that will come over this and come over here. Another another flat sheet over here. So all these secondary structures are linked, right? And they're linked in this really ugly looking way because they keep crisscrossing above one another. When they take these turns, sometimes they don't have any secondary structure at all. They're just free floating. At other points in time, since it's a tight, if you want to make a really tight turn, you can use a tighter helix, which takes turns faster. This kind of tighter helix is ideal if you have a 3-turn helix. So it has some limited application there. Also, you should understand one thing. In an alpha helix, you're getting very few hydrogen bonds. You're getting 4 bonds per turn, right? So when you make just the first turn, you're just going to get the first bond, the first hydrogen bond, the first 4 amino acids. Then you add 3 more amino acids, and they'll form 3 hydrogen bonds with the pre-existing amino acids that were already there, right? If I make my first turn like this, at the first turn, when I've just completed till here, so it's come right round above it, then there's only going to be 1 hydrogen bond over here, right? But once I add this bit, it's going to start pairing with all of these. So for the second turn that I make, for the first turn I make, I get 1 hydrogen bond. For the second turn I make, I get 3 more hydrogen bonds. And for every next turn, I get 3 hydrogen bonds each. What does this mean? This means that just a single turn of alpha helix is not that great, because there's more energy released if it just bonds to the water molecules in the solvent by hydrogen bonding than if it forms a structure. It's only as it gets longer and longer that the stability increases. But a protein embedded in a fat can have a singleton alpha helix. So just remember this, singleton alpha helices never form in water or in the cell, in the cytoplasm. But they can form in the cell membrane, which is filled with fat, where there aren't so many water molecules. So if you're just floating around, you have 0 hydrogen bonds, you form one turn, you get 1 hydrogen bond. Great. Whereas here, if you're floating around in water, you get so many hydrogen bonds with all the water molecules around you. And if you make just a single turn, you just get 1 hydrogen bond. It's not worth making that turn. It's not worth creating that stable configuration. So short alpha helices are always found in fatty domains and not found in hydrophilic domains. Finally, to finish off these helices over here, there's another kind of helix called the pi helix. The pi helix is the inverse of the 310 helix. The 310 helix is one amino acid short, so it becomes tighter. The pi helix has 5 amino acids, so it's a little looser. The difficulty with this is it begins to lose its structure. The hydrogen bonds are less direct, when they're at an improper orientation. There's more steric hindrance. So a pi helix is generally never favorable. By mutation, as a living organism evolves, you might have had some proteins. Some protein made of some amino acids. And then there was a mutation that happened and an extra amino acid got inserted here. Okay. What does that do? It makes the protein looser. This can cause deficiencies in the organism. If the protein is looser, say it's an enzyme that's supposed to bind to some nutritional substance that the animal eats and break it down. Now, it's binding more loosely. So it's not able to break the food down as fast. So this particular animal will eat less in its lifetime. It has a deficit. It has a deficiency in its body. And because of that, it's likely to live less long and to father or mother fewer offspring. And as a result of this, ultimately, the gene that has this mutation for an extra amino acid that's been inserted to make one turn 5 long instead of 4 long in a proper turn, it makes it loose. Okay, this is typically eliminated. So you won't expect to see any pi helices because after a few generations, the gene is lost, right? Except when the amino acid that's inserted offers some bonus in terms of reactivity. Just imagine that loose amino acid somehow actually has a reaction with the food that you're eating, such that the amino acid that was inserted binds to it better. So these pi helices over here, they're only found where the extra amino acid has been inserted over time, despite weakening the structure terribly, has some huge importance in terms of chemical reactivity of that protein. Only then are these not eliminated by evolution. So that covers the lower cluster over here, around minus 55 degrees, minus 60 degrees. Just mirroring the alpha helices which are at the center over here, if I make them positive, those same values, I get what are called the L-alpha helices, the left-handed alpha helices. I already told you that these aren't stable, right? So just pause for a moment and tell me, which amino acid do you think could create a left-handed alpha helix? I hope you've tried. This is why I told you that you should remember certain amino acids. Glycine is achiral. Being achiral, it can form either the left-handed or the right-handed structure. It doesn't make a difference. When we were saying that we have these structures where the R groups are all pointing downwards and outwards, right? It also meant that the hydrogens are pointing inwards and upwards, but we said the R groups have more steric hindrance, and therefore it's better to have them downwards and outwards than upwards and inwards. On glycine, the R group is itself a hydrogen, so both are equally bad. That minimal steric hindrance you get occurs in either sense. So glycine is the only one that can form left-handed alpha helices. Only if a protein is filled with lots and lots of glycine amino acids does it ever assume this conformation. So that's quickly taken care of. The structures here, this pink dot and this orange dot, which I have labeled as PP1 and PP2, are polyproline helices. Okay, these are open structure helices. They're much more open than the ones we covered here. Why are they open? They're open because in a normal helix, I've drawn this too many times now, but in a normal helix, you have this nitrogen with a hydrogen, right? That's bonding to the carbon double bond O from above, or rather, it's bonding to the carbon double bond O below. So this double bond O over here, this double bond O will bond to this H. In proline, there is no H. There's no H because the R group itself bonds back to the nitrogen, and so they form much more open helices if the majority of the protein is made out of proline. One example of a pp2 structure is collagen, which is a very important. It was also solved in India by Ramachandran himself, the guy who developed the plot, and that has three pp2 helix-like structures that are entwined with each other. Collagen is the fiber that helps bind our muscles together, and it's one of the most important things. If you have collagen deficiency, it can cause a lot of muscle deficits. It can cause a lot of ill health. So there are people who have difficulty with maybe they're lacking certain genes, or maybe they're lacking certain dietary requirements that allow them to make this structure. But yeah, and pp1 is even rarer than pp2. pp2 at least forms collagen. pp1 doesn't form any of the normal proteins, the well-known famous proteins. Okay, so that leaves us with something else. This. So I told you that only three structures are going to be important. Hopefully you can guess by now. Alpha was important, the alpha helix. Pi helix was an aberration, 310 was an aberration. L alpha is an aberration that only works with glycine. Okay, polyproline helices, they require high proline density. What is left? These are the two. Okay, so yes, alpha and these two structures actually make up the most. Now, I understand it's possible to be very confused about the letters alpha and beta in this chapter. When we're talking about sugars, they refer to different anomers. When we move to amino acids, they refer to the distance between the amino group and the carboxylic group. At least all of them were alpha acids, so we didn't have to worry about anything else. Here, they refer to a structure, and I'll tell you why in a jiffy. There's a protein called keratin. So this protein called keratin, you may have heard that our nails and hair are made out of keratin, and yes, they are. But this is keratin assuming a right-handed helical or an alpha helical form. But no one knew this. So the protein that makes up our nails and hair was called alpha keratin, because we knew that keratin could form. It was called alpha keratin, and it was one of the two forms of keratin we saw. We knew that keratin could form this tough protein of our nails and hair. At the same point in time, there was another structure called beta keratin, which was softer, as in, for example, silk. And people weren't sure why the same protein could assume these two different textures. Now we understand that this protein is actually helical in such a helix that there's bonding between every fourth amino acid and every first amino acid. And therefore, this structure was named alpha helix in the honor of this alpha keratin. And the flat structure we were talking about was named beta sheet in the honor of this beta keratin. So now I'll just erase the whole thing and we'll look at the two different beta structures. Right, so we've covered a lot of different helical structures. We've covered the alpha helix, which with its perfect I+4 to I hydrogen bonding. We've shortened it and we've got the 310 helix, and lengthened it and got the pi helix. Taking the case of the most flexible of the amino acids, glycine, we have inverted it and obtained the L alpha helix. And by doing the exact opposite and taking the most rigid of amino acids, we've gained this extremely open helix, called the polyproline helix. And as I've already said, there's a protein called collagen that's made out of three polyproline helices intertwined with each other. And this intertwining is possible because of the great openness of the helical structure. We now come, however, to a very different kettle of fish, a very different kind of structure, the beta sheet. The beta sheet is unique and it's different because unlike the other structures, it's not helical. It's flat, it's sheet-like. It resumes cellulose far more than it does amylose in terms of its structure. And a good way to remember this, and this is by pure happenstance, remember, the alpha and beta of these structures is determined with reference to alpha and beta keratin. But the alpha and beta of carbohydrates was determined with respect to the anomeric configuration. And yet, the beta polymer, the polymer with beta linkages of glucose, which is cellulose is a polymer with beta linkages, happens to have a sheet-like structure, and the one with alpha linkages happens to have a helical structure. So that's a really good way of remembering the two structures. Cellulose, beta linkages, flat sheet. Similar structure for proteins, also beta, and vice versa for alpha. So let's look at the hydrogen bonding in these beta sheets in some detail, because they're really quite different from that of any of the helices we've studied. They're of a very different nature, and we'll get into that now. So, looking at the hydrogen bonding of the beta sheet, what we observe is that unlike the alpha helix, actually let's go into the alpha helix a little bit closely first. In the alpha helix, since we have this I+4 to I hydrogen bonding, what's happening is that amino acids which are nearby in the sequence, in the primary structure, are also nearby in the secondary structure. Hydrogen bonding is local with reference to the primary structure. A beta sheet forms something like this. You have this long strand going up, then that strand goes into what's called a coil. A coil or a loop are vague terms in biochemistry, molecular biology, structural biology, biomolecules that are used to refer to a portion of protein or RNA, a portion of protein or of RNA with no specific secondary structure. Okay, so it's just the primary structure floating around, assuming any odd conformation. And then, say we have some helix, and then we come back down to a second coil, and then down to another strand. So this part can be arbitrarily long. The entirety of the protein could rest in here. And yet these two parts, these two strands, side by side, would end up forming a sheet. And similarly, then I can have what's called a turn. A turn is just a 3 amino acid long change and turn around, and then again we go up, and I could have a third strand over here like this. And what's happening over here? What's really happening over here is that again we have hydrogen bonds stabilizing it like this. Just like we had hydrogen bonds in here. One second. These don't co-occur, so it's like. So wherever there are two hydrogen bonds in between these two strands, at the midpoint of that, there's another point that hydrogen bonds to the next strand, and so forth. So these beta strands that form the beta sheet can be really far apart in terms of the primary structure, in terms of the sequence of the protein, and that makes a difference. That makes a big difference to the way these proteins exist. It makes a big difference to how this contributes to the overall structure of a protein, because the beta sheet can bring together disconnected faraway parts of the protein if favorable hydrogen bonding could exist between them, because as soon as those strands happen to fall into that structure, they can't fall back out of it. They're trapped by the hydrogen bonds. So this really is important for the overall structure of a protein. Okay, now let's take a brief look at the exact geometry of the hydrogen bonding in beta sheets. So, there are, if you remember correctly from the Ramachandran plot, two different kinds of beta sheets. There is the beta antiparallel, and over here, of course, we have the beta parallel, over here, up here. Okay, so when we look at the beta antiparallel case, let's see what the hydrogen bonding is like. Firstly, why is this known as antiparallel? It's known as antiparallel because, as you can see, wherever there is an amino group on one of the strands, there is a carboxyl group on the opposite side. And therefore, wherever there's a carboxyl group, there's an amino group, and so forth. Let's see what this means over here, really, okay? So I've got an NH here, and then I've got the R group, the central carbon, the C alpha, and then I have the carboxyl carbon, then I have the next amino acid, next. So clearly, if I go back all the way, this is where the N terminal is going to be. So I have my N terminal somewhere here, because since each of the amino acids is beginning, the N part of each amino acid is here, ultimately when I go to the first amino acid, its N terminal will be hanging loose here, and its C terminal will be hanging loose at the opposite end by the same logic. Now, if I were to just do the same thing for the other strand, we'll see that the N terminal must lie up here, because this is an amino acid begins, central carbon, carboxyl carbon, next amino acid, central carbon, carboxyl carbon, next amino acid. So first amino acid with its N terminal must be here, and therefore the C terminal must be here. And so we can clearly see that these two run in anti-parallel directions. Do excuse me. And this is actually the kind of structure we've shown here, because if this is the N terminal, then finally this will be the C terminal. So we go N and C and back. So actually it flips in direction. Now let's see what happens in this particular case. Wherever I have an NH facing inwards, I have a double bond O facing inwards on the other side. I have a double bond O facing inwards on this side. I have an NH facing inwards on that side. Okay. There are, however, these regrettable occasions when you have the two R groups facing inwards. But that is also somewhat mitigated by the fact that these do not point in the same direction. Because all the amino acids are L in their configuration, because this structure and this structure are mirror images over effectively. I'm not talking about the exact R's over here. There will be two different R's, so there won't be exact mirror images. But this skeletal structure is mirrored here. So the R groups will go in opposite directions. One will come out of the plane, one will go into the plane. So there's far less collision. And there are these perfect hydrogen bonds. So what generally happens is you have two hydrogen bonds, then you have two R groups, two more hydrogen bonds, two hydrogen bonds, then an R group, almost collision. Two more hydrogen bonds, another R group, almost collision, and so on and so forth. This means, if you remember, there was this big blotch on the Ramachandran plot in the upper left quadrant, the second quadrant of the Ramachandran plot. And the reason for that is that these can occupy various dihedral angles, as long as these bonds can form. Okay. Also, you can see that I have these free bonds on either side, and they can bond on to similar sheets, the similar strands that form like this. Okay, that is the beta anti-parallel case. Now let's take a look at the beta parallel case. This is the beta parallel. This is the beta parallel case. Now in the beta parallel case, we can clearly see that they're going from N terminal to C terminal, both of them together. The R groups point in the same direction, so there's a chance of collision. You may say they look very far apart, but remember this is not to scale, and the R groups are long, so there always is a chance of collision. Even if they're both pointing in the same direction, either left or right, they're also pointing either both up or both down, so they can get entangled in each other. There is this chance of, how do I put this, the two of them getting hit. And the angle of the hydrogen bonds is different over here. Let's take a close look at it. Okay, here we have this double bond O, and the NH is down here, so this is the hydrogen bond. And here we have a double bond O, and its NH is down here, so this is the hydrogen bond. So we have these what are known as wide pairs of hydrogen bonds, because if I were to extend this and extend that, they form a very wide angle, whereas these two, don't form any angle at all. The hydrogen bonds are parallel in this case. So the hydrogen bonds should be over a larger distance, a diagonal, as opposed to a single parallel, as opposed to a shorter distance between these two, because of the parallel configuration. That should imply logically that they're weaker because the hydrogen bonds are further apart. Indeed, beta parallel is what we get silk from. Okay, so it is the softest of proteins in some sense that form from a beta parallel sheet, because you would think that they can be torn apart very easily. And therefore, you might be tempted to think that beta anti-parallel is more stable than beta parallel. But I should warn you that that is not entirely substantiated by science. We're still not sure which of these two structures is more stable. We do know that this is much more picky in terms of the angles it gets. It has to be, if I remember correctly, minus 135 degrees, comma 135 degrees, phi comma psi. It has to be at this location. That was the sharp point on the Ramachandran plot that was surrounded by this cluster, and that was the beta parallel sheet. Now, why do I say there is this dispute? And by the way, if you can't see why these have to be the case, I encourage you to pause for a moment and think about it. Okay, so the reason that there has to be specificity in terms of these angles is because otherwise these R groups would collide with each other very, very strongly. Only if they're at more or less the right angle, at a particular angle value only, is there not going to be that collision. So the dihedral angles are particularly important for the beta parallel case. Now, why do I say that there's controversy over which is more stable? I say so because there is controversy, but the real reason underlying it is that though these beta anti-parallels are far more common, when you have very, very few strands, just 3 or 4, maybe 5 strands, and not 10 strands or something forming a beta parallel sheet, then you typically see a beta parallel forming, not a beta anti-parallel. So you would assume that when the one that releases the most enthalpy of formation, or rather the enthalpy of folding in this case, the one with the higher enthalpy of folding being released is the most stable one in thermodynamic, as per thermodynamics. And then this seems to be taking the cake, because when you have very few of them, this is stable. Only when you have very many of them and you have many hydrogen bonds forming, like it goes on for strand after strand after strand after strand, does this become common. At the very smallest amount, this is more common, and we're not quite sure why, because as you can see, the hydrogen bonds appear weaker because the dipole attraction is over a greater distance, and you can do Coulomb's law, Q1 Q2 by R square, and you can see that a greater distance should be weakening the force. But we're not entirely sure why this sort of thing does take place. Okay. Now, there's one exercise I should probably have asked you to do before, but you might as well do it now. I'll just move aside. You pause the video, look at the two, and check for yourselves that these are valid protein structures. Okay, I hope you've done that. Now we've got these two structures. Now let's move on to the very last part of the beta sheet structure, and that would be the kind of amino acids that favor this structure. Which are the amino acids that have the right dihedral angles and whatnot? And why would they favor this structure as opposed to forming an alpha helix? Well, the answer is very simple. We form this structure when your R groups are split at the second carbon, or they are aromatic. So remember, the second carbon is always this carbon over here is called the first carbon, and the first carbon of the R chain is called the second carbon. It's called C beta, but there's too much beta going on here, so I won't throw that term around. So the second carbon over here should be branched. This is why I had underlined certain amino acids when we did the list of all amino acids. I had underlined valine and threonine and isoleucine because they were branched at this position. Because they're branched at that position, they can fit together very nicely. If it's very, very long in terms of a chain, then they would still go up and get entangled. By moving one of the substrates down a little bit, we make it shorter. So the chance of this entanglement is less, that this goes up, but then it turns downwards at some later carbon, and they still get entangled and have steric hindrance. On the other hand, if I were to form an alpha helix with a branched R group, then one branch could go back into the helix. Remember, the whole point was the R groups go outward and downward. But when they start branching, they can interfere with each other and cause more steric hindrance. So the branched R groups are not favored by the do not favor the alpha helices, especially when the branch is only the second carbon. The same logic more or less is true for the aromatic amino acids which we've discussed, like tryptophan and phenylalanine and all the rest of them, tyrosine, histidine, all of those. Okay, so that tells us what kinds of amino acids are favored for the middle of the beta sheet. Okay, something else that's very important you should know. Proline, our favorite proline, the most rigid and inflexible of all amino acids, has a major role to play in beta sheets as well. Proline forms at the edges of the sheets, the last strand. Let's just assume this is the last strand on this side, and this is the last strand on this side. So it's only a 3-stranded beta sheet, let's assume. Then there will be a bunch of prolines here. And a bunch of prolines here. There could be. There are sometimes other amino acids also that do this, but proline definitely does the best job. What does this do? Proline does not have an NH group. It has an N, but no H, because the R group is bound back to the N. The missing hydrogen means that proline does not form further bonds on this side or this side, and therefore the beta sheet is trapped at a certain point. If we don't do this, we get into a very dangerous territory known as amyloid formation. Okay, I'm just going to cover this in brief. I'm not going to write anything about it. Just give you a quick oral presentation, maybe 20 seconds or so. Amyloids are what happens when you have this beta sheet that just keeps aggregating and aggregating and aggregating. As your cell produces more and more of the same protein, sometimes if that protein is folded up in a beta sheet without this kind of proline type guard on the side, then another protein's the same part of another protein could get added onto this beta sheet. The beta sheets keep aggregating, and it grows into this large mass known as an amyloid or an amyloid fibril. Why is this dangerous? Amyloids are behind all kinds of diseases, such as mad cow disease and possibly even Alzheimer's, because there's a protein called amyloid beta, which is obviously an amyloid. By the way, it's also a beta sheet, because amyloids have to be made out of beta sheets. And so these have been seen in many diseases, including specifically neurodegenerative diseases. There are also certain organisms that actually use amyloid formation as a protective covering and such, but generally you usually hear of the bad ones, which are also called prions, if you want to know the term. So this proline guard is really important to prevent that. And now you know pretty much everything you need to know about the secondary structure of proteins. I want you to remember three major things: the structure of the alpha helix, the structure of the beta parallel sheet, and the structure of the beta anti-parallel sheet. Pi helix, theta helix, yeah, all very good. Probably won't come directly in a question paper. You might get a comprehension where they explain the thing to you and then ask you to answer it. And if you're already familiar with it, good for you because you know the topic. It's not going to come in a direct question. Alpha helix, beta parallel, beta antiparallel, they can easily come in direct questions. So please remember these. So I'm sure you're thinking now that we're done with the understanding of proteins. We know what their primary structure is, and we've even studied some weird, high-level, academic sort of classification of what their conformational isomerism is like. Some fancy way of doing it, yeah, a lot more conformations than we had to remember, but given the millions of atoms in there, probably a plus side that there is 5 or 6 conformations, not much more than cyclohexane or some such thing. But we're not done. Proteins are humongous, and there are additional levels of complexity even above the secondary structure. Thankfully, we don't have them in too much detail. And remember, even the secondary structure, while it was taught to you in a lot of detail so that you understand what you're doing and you understand where it comes from, just from dihedral angles, you only have to remember the alpha helix and the beta sheets. But when it comes to the tertiary structure, we're going to learn just a little bit more. So, let's say you have a straight chain like this, then it goes to a very sharp turn, say a 310 helix, and goes to another straight chain, and these two might form a beta sheet. Maybe it goes to a long coil, comes back, continues the beta sheet, then goes into an alpha helix, then goes to some other kind of chain, so it carries on like this. But this entire structure with the beta sheet and the helices and all of it can fold upon itself. The different secondary structural elements of the tertiary structure can all occur at different parts of the three-dimensional space that the protein occupies. This is known as the tertiary structure, and it comes in two major variants. There's the fibrous variant and the globular variant. The fibrous and the globular. Okay, the fibrous is long, tough, and generally speaking insoluble. We have that same old example of keratin here, okay, which we studied for so long. And globular proteins like say hemoglobin, that's where the globin comes from, by the way. Hemoglobin, okay, these are round in shape, and they're water soluble. They're water soluble because it forms a globular shape, and all the parts on the various secondary structures, all the different amino acids which are hydrophilic are exposed on the surface. Now the hydrophobic ones are deep inside it, and that allows the whole thing. So it allows for the outside to get tugged into the water and for the whole protein to be dissolved into the water by forming a really large solvation shell, but prevents the protein from losing its tertiary structure because the inner parts are hydrophobic and avoid the water molecules. Okay, now let's study a few of the forces that are responsible for creating this tertiary structure, and then we'll wind up with this tertiary structure thing by looking at one particular example of a tertiary structure. So, one is dipole interaction. So dipole interaction is fairly easy to understand. We saw that a lot of our amino acids were polar. This polarity determines this hydrophobic thing I was telling you about. So it determines whether it can be globular or not. If it's not too polar, not too non-polar, it can form this fibrous kind of chain. So yeah, it depends. The polarity is a big factor. It decides what amino acid attracts what other amino acid. And if a set of amino acids in one secondary structure attracts another set of amino acids in another secondary structure, the two pair up together and the tertiary structure begins to form that way. Okay, That's simple enough. Another thing is again hydrogen bonds, but this time from the side chain. Remember amino acids like tyrosine or threonine or serine that had all those OH groups sticking out here and there? Or even for that matter, your charged amino acids. They too can form these kinds of hydrogen bonds. Those are actually called salt bridges, when the hydrogen bond forms between charged amino acids like say aspartate and arginine, where arginine has a plus charge and aspartate has a minus charge, because they have an ionic interaction and an H bond. That's called a salt bridge. It's not in syllabus, don't worry about it. So you can form these side chain hydrogen bonds. Why is it specified as being side chain? Because the atoms, the groups of the backbone, like the amino and the carboxyl, which are part of the backbone, do not undergo any kind of hydrogen bonding. What undergoes hydrogen bonding are the side chain bonds. A third source of tertiary structure is are coordinated ions. So coordinated ions, for example, there's this one. There's this one particular bacteriophage or virus that infects bacteria that has this prong-like thing at the bottom of the virus. So let's just assume this is a T4 bacteriophage. If drawn it really badly, it has this prong, and that is used to infect a bacterium. This is the bacterial cell. So this prong, this proboscis-like thing, plunges into it, but it's really, really small. This is the level of molecules. Viruses are just large collections of molecules. How does it get this sharp protein? Because this is, after all, just a protein, this prong of it. It's got 3 alpha helices. Each of these has 3 histidine residues, and those 3 histidine residues are bound via coordinate bonds. They form a metal complex with a zinc ion in the center that pulls them all together and gives it that sharp shape with which it can stab a bacterium open. So coordinated ions have a very important role to play. And the final determinant, the disulfide bond, is what we're going to study an example which is in portions. I gave you this example too, but that was just as an illustrative one. This is actually in portions. So what is this example? This example is the example of the disulfide bond. Now recall the disulfide bond from the talk about cysteine. Go back and watch that part of the video if you've forgotten it. Okay? So let's say I have this is the structure of insulin. We visited insulin so many times now from the carbohydrates part onwards that I don't think we need to talk about it much. If you don't remember, it's the thing that would direct the conversion of glucose into glucans like cellulose, or no, not cellulose, not in us, but fat or glycogen. So this is that same hormone, which is actually a protein-based hormone. And it has 3 different disulfide bridges. Okay, what happens is this is actually what's called proinsulin. This is the protein that our cells produce. But then this part is not needed in the final functional hormone, so it gets cut out. So what keeps the whole thing together? Let's look what the final version looks like. In the final version, it just looks something like this. So what keeps this together? 2 disulfide bridges link these 2 parts of the protein with this one part of the protein. And an additional 3rd disulfide bridge lends it its structure. This has come once in a JEE paper where they ask how many disulfide bridges are in insulin. If you remember this thing, that there's this whole chain and we have to cut out a bit, you can easily guess 2, because to attach it to the other chain and make sure that these bits don't just fall off, there must be something attaching it to the other chain, so there must be one on either side, so there's 2. But there's this additional 3rd one for rigidity. Do not forget this. It's come once in JEE, so it probably never will come in JEE again, but it could be recycled into other papers. So you should remember this. Insulin has 3 disulfide bridges. Okay? Now that brings us to a conclusion of the topic of tertiary structure. So now we're going to move on to the next level of structure. And yes, there is another level of structure. The most complex of them all, quaternary structure. I must emphasize, by the way, that there is a very distressing tendency of students to call it 1 degree, 2 degree, 3 degree and 4 degree structures, especially students who are not accustomed to studying much of biology or chemistry, But please remember that these are pronounced as primary, secondary, tertiary, and quaternary. 1 degree, 2 degree, 3 degree and 4 degree will probably get you slapped by your teacher. So, coming to this quaternary structure, what really is it? A quaternary structure when you have multiple polypeptides, multiple polymers of amino acids with their complex peptide backbones and the dihedral angles and all of it, which are bound together. The same forces which bind things together in the tertiary structure is also considered in the quaternary structure. In fact, you could argue that what we studied of insulin was a quaternary and not a tertiary structure. But generally speaking, that is the one exception. We do not count disulfide bridges as being the forces responsible for quaternary structure because disulfide bridges are covalent. But the other things, dipole moments, coordinate bonding, etc., those non-covalent interactions are very important for what we call quaternary structure. They allow two different polypeptides to get entangled together, okay, and that gives rise to this much larger protein. So proteins can be polypeptides, as we studied before, or they can be complexes of polypeptides stuck together. The word for an ordinary protein, like we said before, is called a polypeptide, as I've said many times, and the word for larger ones is a complex or a protein complex. So I've given just 3 examples of protein complexes, and that's all that we need to know. One is the histone octamer. It's as it sounds. It's a protein called a histone, and it's an octamer. There are 8 of them. This is used in DNA packaging. DNA packaging. We know that there's a lot of DNA in our cells. It could go to the sun and back thousands of times if we took all the DNA in our bodies. It's that long. So what keeps it all packed up nicely together? These histone octamers. They're very important. And as it says, they're octamers, so that 8 different things bound together. Then there are viral capsids. These can be up to 60. No, I think these are often 60. They can be even higher. So often 60 different polypeptides all tied up together to create a protein coat around a virus. The protein coat in biology is called a capsid. And finally, the stereotypical NCERT example, hemoglobin. We've just said before, it's a globular protein, and it has 2 subunits that have an alpha group, that have alpha secondary structure, and 2 more subunits that have a beta secondary structure. But all these subunits are coordinated and attached, so they're attached to this group called a heme group, which is itself coordinated to an iron ion. And so, by attachment to the heme group, attached to heme group, they all get connected, and therefore they form a quaternary structure, which is that of hemoglobin. And that ends the discussion on quaternary structure. Having finished and disposed with the structure of proteins, we can move on to one of their specific functions, enzymatic catalysis. Right. Now, enzymes are exciting. Enzymes are molecular machinery. Enzymes are these huge factory-like things that churn out millions upon millions upon millions of molecules per minute. And they catalyze reactions faster than any known artificial catalyst. Okay? These are something to be wary of. These are something being applied nowadays. We're taking bacteria that have an enzyme that can catalyze some reaction we're interested in. Say the degradation of some product. Say we've found some bacteria. Let me give you a hypothetical scenario. Some bacteria has evolved that can, to some minor extent, degrade a variety of plastic. Okay? We take this bacterium, we grow it in large numbers, we use gamma rays to attack it. Some of them go full Hulk on us, okay? And that enzyme gets better and better. It can degrade a particular variety of plastic. We start taking the enzyme out, and we have something with which to degrade plastic. This is a very simple schematic, but this is actually how we're beginning to harness enzymes today, and we're beginning to understand their power more and more and more. Okay, if you want a good understanding of this, I recommend that you go on YouTube and watch the watch the song video called Nanobot. It's a parody of Havana, and it's on a channel called A Cappella Science. And on that channel, they've done a really good job of showing how nanobots work, small nanoscale molecular machines. And you will see that the highest ones they approach, the later ones, are all enzymes. They're all biologically engineered ones. So this is important. We're trying to copy this artificially, haven't got that far yet. Often we're evolving organisms and stealing their enzymes to do the job. Okay, so let's study some basic characteristics of the enzymes. This really falls into molecular biology and not biomolecules, but it's mentioned briefly in the book, and I'll mention it equally briefly, except for when I wax eloquent about how great they are. So enzymes are extraordinarily selective agents. Okay, they fit and act with only one particular kind of molecule. This is known as the induced fit of an enzyme. If this is what an enzyme normally looks like, okay, let's just assume that this is a tertiary structure of the protein, and then this is the substrate, the thing that's going to act upon. The substrate gets in here and induces, it causes the enzyme to change its shape until the enzyme fits around the substrate exactly. They interlock. When this happens, this is written, by the way, with the following notation: enzyme plus substrate gives rise to an enzyme substrate complex. This is a symbol for a complex. Okay, we already discussed what protein complexes are. Now this is a similar kind of complex. The substrate need not be a protein. It could be any kind of molecule that this enzyme is acting on. Sometimes it could have two such pockets with two different substrates. Maybe it's got to combine these two. Maybe it's got to, for instance, say you take maltose and water, you combine and break it onto two glucoses. There's an enzyme like that. It's called maltase. Okay, and these pockets are known as active sites. Active sites. These are active sites. This is where the enzyme goes and it gets to the stage ES complex. But then it moves on to a different stage. It catalyzes a reaction. Either when both of these two substrates fit in, they induce a change. Like once the first one comes in, it just induces a fit. When both of them are in, it induces what's called a conformational change in the enzyme. You heard that right. Secondary and tertiary structures change and they smash these two together. Okay, so the maltose hits the water, it undergoes hydrolysis, and we get our basic molecules, the two glucoses. Okay, so that is how this works. What we get then is the enzyme product complex, and this is much less stable than the enzyme substrate complex. So whereas we had this K value, we had a K value, say K1 for this reaction. Okay, let me make it bidirectional. Okay, if this is also going to be a bidirectional reaction, then the K value, K2, is much lower. In fact, it favors it when it's broken apart. So it favors enzyme plus product separately, not together. And that is what lets us get this product out. So there's this constant chain going on with various equilibria, with various changes. But the most important thing to notice is that if you've already studied surface chemistry, you know that a heterogeneous catalyst works by having a little pocket into which things fit, an active site. Okay, now this does have active sites, and yet it's in the same phase as whatever it's reacting with. So it's molding and changing its shape. It's creating an active site to fit the substrate it's acting on. This is extraordinarily unusual, and this is why they are so fast. Enzymes can catalyze millions to tens of millions of molecules of substrate per second, and they do this in two different ways. They can either capture both the substrates and hold them nearby so that their Brownian motion is reduced, or the bonding to the substrate could be such that when it attains a transitional state during the reaction mechanism, that transitional state is stabilized by its enzymatic surroundings. So this covers the first 2 points. The next point is that it has an optimum pH and temperature. This point I could have taught you earlier when we were talking about proteins in general, but I reserved it for now since it's so very relevant now. So let's see what it implies. Okay, let's say that I have this graph like this, and there's an increase in pH over here, and what we're looking at is how fast the reaction takes place, so the rate of reaction catalyzed by the enzyme, and we get a curve like this. Okay, so what we clearly see is that the enzyme at very low and very high pHs is barely working at all, whereas at some optimal pH it's working just fine. And this optimal pH is the pH that the cells of that organism are normally at. That's why the enzyme has evolved to work best here. Something very important happens when it goes off to either of these extremes, something called denaturation. We're very familiar with this. When you add an acid like lemon juice into milk and you boil it, so you subject it to low pH and high temperature both at once, the milk protein gets curdled into curd, right? Or the basics of cheese. That's how we make paneer at home. So denatured proteins are just that, the proteins that lose the secondary, tertiary structures. They only have the primary structure left. Cheese is denatured. Egg yolk, once you've cooked it and made it an omelette, is denatured. They lose their basic properties. They lose their secondary and tertiary structures. And this happens with an increase in pH or a decrease in pH. Okay? If I were to replace this with temperature, the cool thing is that the shape of the graph is more or less the same. The shape of the graph is more or less the same. The only difference is that denaturation occurs mostly at the higher temperature. What happens at the lower temperature is that the temperature is too low for the reaction. Because we know that most of these reactions, when you get higher temperatures, they work better because you speed up the reaction, right? So it just happens that the temperature is too low, it's too cold, not enough things moving, the reaction doesn't take place. It's as simple as that. Okay, so these are the graphs of pH and temperature. You should know these graphs. Very simple, very easy. The next thing we have to study about enzymes is a process called inhibition. To understand inhibition, I have to introduce another concept to you. Alongside the active site, we need to now study the allosteric site. Now, I must remark that I'm going really fast because there are very few things to be taught about each of these concepts. But since there are rather a lot of concepts, it would be very good if you were to rewatch the part of the video about enzymatic catalysis. It would be good for you and you'll be able to have a better understanding of it. So once I've done watching this, you might want to watch it again or watch it again before exams at any rate, this particular part. Unless, of course, you're a biology student and are familiar with all this. When we talk about the inhibition, we have this enzyme. Here's the active site. And here's the allosteric site. Now, allosteric site comes from the Greek word allosteros, which boringly enough means other thing. So this is the active one and this is the other one. So the allosteric site and the active site. Now, two things can happen. The allosteric sites are basically pockets. When something fits into them, it changes and messes up the shape of the enzyme. One thing that can happen is, this is your substrate S, and there's a competing thing that looks very similar. I'm going to denote it by sigma. This competing molecule that looks very similar goes and gets stuck in here. And when that happens, this S cannot get in. And so it can't react. Most toxins and poisons work this way. They have a compound very similar to some substrate for one of our enzymes. And unless that enzymatic reaction goes on, we can't live. It's something crucial to us. So the poison has the compound that goes and it actually binds to this better. Sigma binds better than S to our enzyme. And so S can't bind. And yet, sigma can't undergo the reaction and become a product. So what happens is the enzymes get blocked, the crucial action doesn't take place, and we die. This is known as competitive inhibition. Maybe I should use the other color, the allos color. So this is competitive inhibition, and there's also allosteric inhibition, which is what happens when some other thing, let's call it X, comes and fits into the allosteric site, and that causes, again, it induces a conformational change, and this pocket becomes, wait, this is looking really messy. Right? So what happens in that case is that this pocket becomes either too loose or, let's say for this sake, too tight, too small for S to fit into. So we change the conformation so S can no longer fit in, and we've allosterically inhibited it. Now, allosteric inhibition is generally not something that comes from outside. Generally, allosteric inhibition is something that is done by the body itself to keep an enzymatic reaction in check and to keep it from going too fast. Okay, when we don't need a particular reaction, we inhibit half of it using this allosteric inhibition. Similarly, we can promote enzymatic reactions by the use of other allosteric promoters, okay, allosteric regulators, like calcium ions, which are essential for the movement of our muscles. All the waving about I'm doing right now, it's because of floods of calcium ions going and attacking allosteric sites along my myosin fibers. So this is important. Now, Cofactors, the last things mentioned here, what are they? They're not like coefficients, they're not factors that are alongside something else. They're not mathematical at all. A cofactor is some factor S, X, but not necessarily an inhibitor. A cofactor is the very opposite of an allosteric inhibitor. It is an allosteric necessity. An allosteric necessity. If it isn't present, then this particular protein will not have the right shape at all for the substrate to react with it. So unlike an allosteric inhibitor, which causes the wrong shape, the allosteric necessity, the cofactor is necessary to keep the right shape. Cofactors can be inorganic metal ions. They can be loosely attached coenzymatic molecules, the organic molecules that come in and go, or they can be tightly bound prosthetic groups. Okay? So, inorganic, coenzyme, and remember a coenzyme is organic but loosely bound, and a prosthetic group. One example of prosthetic group, albeit not for an enzyme but for an ordinary protein, is the heme group we discussed earlier, which is part of hemoglobin. And that heme group itself is coordinate bonded to an ion, which is an inorganic cofactor. So we already have these two different companions to a protein. Hemoglobin is not an enzyme, but it is still a very good example of what this means. I hope you understand what I mean by prosthetic group, like a prosthetic limb. When you get if you happen to lose your arm, say in war, and you have a prosthetic limb attached, it's permanent.
Okay, so now I have to teach you something that's technically doesn't fall within the province of chemistry at all. Only in exams that do not include biology, like say JEE or something, you might have some vague question mentioned like the absence of this enzyme causes which disease, and you'll have to know it. Okay, it's purely biology. It doesn't fall within the province of biomolecules or the province of biochemistry. But because there have very occasionally been questions, I am covering it. Okay, this is not biochemistry. This is proper biology. Okay, it's just 3 points. Bear with me. It has to do with protein-related diseases, specifically when there is a mutation that causes the protein to have the wrong structure and therefore assume an incorrect form. We have these are 3 examples of the diseases that can result. One is when we do not have phenylalanine, this PAG is phenylalanine hydroxylase. Hydroxylase. So when we do not have phenylalanine hydroxylase, we suffer from phenylketonuria. This is a sad, sobering disease. You have it from childhood. Your teeth fall out early, your hair gets discolored, your face gets wrinkled, your body doesn't work properly, your tissues are malformed, your mental development is retarded. And the reason for that is this, because phenylalanine, which is one of the various amino acids we have, can be toxic to the body. It can disrupt various functions. So the phenylalanine hydroxylase adds a hydroxide group to phenylalanine. Do you remember what phenylalanine was? It was NEPH, right? It was Ne with a benzene group. Now, when we have the same benzene group with an OH, that's tyrosine, and phenylalanine hydroxylase actually adds this OH group, makes it tyrosine, which can stay in the body more or less harmful. However, even this tyrosine is something that you need to be able to degrade properly. In fact, people who have a lack of the enzyme tyrosinase suffer from a less harmful condition. Okay? People who don't have tyrosinase suffer from a condition that you have heard of, albinism. Okay? It's one of the ways that you can call albinism. You can also be born without any melanin at all. Albinism is people who don't have melanin in their skin. So a lack of tyrosinase can cause a whole bunch of chain reactions and end up leading to a problem in synthesizing the melanin in your skin. Or you can just have a lack of the proteins that actually code of the genes that actually code for the proteins that make up your melanin. Essentially, you have no melanin in the skin, completely white, easily sunburnt, etc. Okay? This is to be different from a Caucasian white person who does have a certain minimal extent of melanin in his or her skin. finally, we have sickle cell anemia, which is unlike the other two, not enzyme linked at all, rather it has to do with hemoglobin. Hemoglobin is abbreviated HB, and this is something you should be familiar with now, because I'm just going to use it everywhere to finish this last point. This is the normal shape of the Nakema man. So this, the biconcave, is the normal shape of an RBC, red blood cell. Okay? Now, you have hemoglobin within this. Cool. When you have sickle cell anemia, there is a mutation in the hemoglobin that allows it to form a covalent linkage with another hemoglobin. When you have a long such chain, it becomes quite stiff, and this red blood cell changes in shape, and it becomes sicklish. This does not mean that it becomes into a communist. What it means is that it acquires this shape like a blade of a sickle. This is a problem because when you have two such sickled shaped cells passing through a tight or small blood vessel, they get entangled and lead to a block, a buildup. And then they are unable to travel to the lungs and go and acquire oxygen and do the normal duty of red blood cells. So it's very dangerous. It can even be fatal. This gene is very common in sub-Saharan Africa. Why, you might ask? Why would this not be eliminated by that most glorious of all natural forces, evolution? The answer is, evolution chose to give humanity, specifically humans from sub-Saharan Africa, riscus sort of as a replacement for a much worse. Let's see how it works. This is for all of humanity, not on an individual per human basis. Let's assume you only have this defunct hemoglobin, so maybe as hemoglobin star, in a couple of places. Okay? How could that be? If you got the gene that makes the defunct hemoglobin, the hemoglobin tends to polymerize and attach to other hemoglobins from one parent, so your mother or father, then some hemoglobin will be defunct, and the rest of it, producing the other gene, will not. Okay? Simple enough. The defunct hemoglobin will cause some things, but because of the presence of normal hemoglobin, the chains will be limited in size. This adds a certain stiffness and makes it hard for Plasmodium vivax to break into your red blood cells and turn this hemoglobin into a dangerous toxin called hemozoin, which is responsible for malarial fever. Let's assume now that you have a population, an entire population, okay? An entire population that has the gene that's called capital H for defunct hemoglobin, and from one other parent has the gene for normal. Okay? Remember the old Mendel process during class 10 where he mix these up. Okay? So one child might get only normal hemoglobin. Therefore, they're not malaria resistant, but they have the normal hemoglobin. It doesn't change them at all. Okay? Now you could get the defunct hemoglobin from the father and the normal hemoglobin from the mother, or you could get the normal hemoglobin from the mother and the defunct hemoglobin from the father. And only 1/4 of cases do you get both defunct hemoglobin, which chain up completely and make it so rigid we enter sickle cell anemia, which means that half of the children of the population are resistant to malaria and only 1/4 die of sickle cell anemia. And because this 1/4 die off, they are trying to become parents in turn. So their kids are not likely to suffer from this. And these are not malaria resistant, so they are also going to die in high numbers. So these are the ones that survive. And so on average, the human race in sub-Saharan Africa does better because they are malaria proof. Of course, in today's day and age, we have a lot of anti-malarial drugs, and so this is now unequivocally a curse. But back then, from the evolutionary standpoint, to keep the species going, this is the mutation that ended up being favored by the force of natural selection. And that is why we are living this terrible curse today. In increasingly interracial worlds, people migrate from one part of the world to another. These genes are spreading, and our proteins are therefore increasingly diverse all over the world, regardless of whether you're from sub-Saharan Africa or not, because you might easily have an ancestor who was from there. This brings us to a conclusion on the entire large section of proteins. I hope you learn to appreciate them. They are the basis of our structure. They are the main catalyst that gets things done. And when things go wrong, they can go cataclysmically wrong, as we've seen. They have chirality, yes. They have secondary structure, yes. And these chemical things are very important for you to remember. They are the future of a lot of chemical engineering and nanotechnology as we try and base up our molecular machines of these proteins. Okay? And now, I'm done with them, and we will move on in the next video to the section on nucleic acids. Thank you.